Hello friends, welcome to another video on my YouTube channel. As I have mentioned earlier, I will be moving all my sketching content to a new channel, Shades on Canvas. I'll post a link to that in comments as well as in the description. So let's start today's video on HTTP3. As in our previous video, we have learned about HTTP2, right? So there are some features about it. So it makes use of multiplexing. In multiplexing, it can use a single connection to make parallel requests. Unlike HTTP1, where it needs to create multiple connections for parallel request, it can use only one connection for that. It only uses one TCP connection, and it fixed the HTTP head of line blocking problem, because in HTTP head of line blocking with the connection only one request was possible, right? So if the client wants to make another request on the same connection, it has to wait for the previous request to get finished. So that was the problem in HTTP1, which HTTP2 resolved by the use of multiplexing. But HTTP2 still suffers from TCP head of line blocking, as I have explained in the previous videos, HTTP1 as well as in HTTP2. In TCP, once a packet is lost, all the streams were affected until unless that packet got retransmitted. So it still suffers from that, and HTTP3 resolves that. We will see in the video how it resolves it. So as the packet loss rate increases, HTTP2 performs less and less well, because as more packet will get lost, more streams will get blocked and performance will drop down. So it depends on the packet loss. Now, as HTTP2, as we know, uses the underlying TCP protocol. So TCP is a protocol which is used for reliable transfer. Basically, TCP is used where you want some sensitive data, and you want 100% guarantee that your data will be transferred as it is. There will be no packet loss or anything. In that case, TCP is used. So till now, HTTP protocols are using TCP protocol as an underlying protocol, and that is the main reason they suffer from head of the line blocking. It's not a limitation of HTTP; it's the limitation of TCP. Until unless there is a TCP protocol in the downstream, the head of line blocking will still be there. So that is why HTTP started with the UDP protocol. So as you know, if you have learnt about TCP and UDP protocols, UDP is user datagram protocol, and it doesn't have those many restrictions while transmitting the packets. In UDP, it's possible to get it's possible for some packet to get lost, but it doesn't block the streams for that. So to remove the TCP head of line blocking, HTTP3 started using UDP in the QUIC protocol. So basically, they created a protocol QUIC, which in downstream uses a UDP protocol. With QUIC, there is still a connection set up between two client and server. So there is a client and there is a server, like in other HTTP protocols, and there is still a connection going on between them. So there is a packet transfer, initial connection setup, where a packet is transferred from client to server. Then the server responds to the client with some secret, and client acknowledges that. So there is a connection set up in HTTP3 as well, but in this, as we are using UDP protocol, all the streams are not depending on each other, as like in TCP, because TCP has restriction on the transfer of packets. So when a packet gets lost, it stops every stream, right? But in UDP, once a packet gets lost, other streams are not affected by it. Only the stream in which the packet loss has happened will be affected by it. So in this connection, when QUIC uses UDP, all the streams are treated independently. So let's say there are two streams going on, one with this yellow color and one with this blue color. Let's say these streams are handling two different request response pairs. So let's say in both the streams, data is going from client to the server, and let us say in the yellow stream, the packet loss has happened. So only the yellow stream will get affected, but the blue stream will continue to send receive data from the server. Because here we are using UDP, so all the streams are not affected, and these streams are treated as independent streams. Now, as we know, from the previous video of HTTP2, there is also a head of line blocking on headers as well, right? So as you know, in the HTTP2 uses two types of tables, static and dynamic table, to compress the headers, right? And once let's say dynamic table is used for the headers that are dynamically sent during the runtime, when the request response happens. Whatever the new headers are sent, those headers are entries for those header is maintained in dynamic table. Static table is used for all the common headers that is being used by all the requests most of the time. So once a new header is sent, one frame is sent for with the header details, and then after that all the requests will use the index entries for those updated headers, right? So in HTTP2, once the let's say the packet that has the header info that gets lost, then all the other streams will get affected, right? Because they will be sending index value which the server will not be able to recognize until unless the frame with the header values reaches to the server, right? So that is the head of line blocking on header compression in HTTP2, right? So here instead of HPAC, HTTP3 is using a QPAC to encode all the headers. So here the compression and everything is still same, like it is headers are compressed and they are maintained in the table, and they are maintained in a table, and only the indexed entries are going in the request, but the compression technique is different. So instead of HPAC, HTTP3 uses the QPAC protocol. In this QPAC allows header table updates and header blocks to be sent on separate QUIC streams. So in this because of the independent streams, QPAC allows the data of header and allow the header updates and header blocks to be sent on different streams. So as the streams are independent in HTTP3, let's say header fields can reference entries in the dynamic table, but even if the decoder hasn't received the updated table yet, it buffers the header block until the entry arises. So here, as the streams are independent, so it could happen, right? So in the frame in which the entries are going, the new entries are going for the dynamic table gets lost, and the another streams are sending the index values, the values that should be present in the dynamic table, right? So the server or the receiver, whoever receives the packet, will not be able to recognize those entries, right? So it will just block those packets until unless the entry arrives on the server side. The difference here is in the HPAC, once the packet is lost, other packets are not even sent by the sender. So let's say the entries of the header update frame is lost, then all the other streams will also get affected, right? They will not even set those index entries frame. They will not set other frames with the index entries, right? They will have to wait until unless the lost frame is retransmitted to the server. But here the data will keep on coming to the receiver, and if the receiver receives a packet that contains those indexed entries and it doesn't have the updated table yet, it will just block those entries, and when that packet will be retransmitted for the header entries, then it will unblock them and serve the request. So it also uses the same Huffman coding to compress the headers. There is no difference in the algorithm, which is basically the Huffman coding algorithm, which is used in HPAC as well as in QPAC. But the difference lies not in Huffman coding, but how the header compression and state synchronization are managed between encoder and decoder. So, and the only difference here is to explain it how the entries are managed in the table and how the syncing of entries happen between a client and the receiver, so that both are aware of the same encoding and they can decode the encoded entries that are coming in the header fields easily. That is all is different in QPAC. Now, congestion control is similar to HTTP2. It also provides congestion control as in HTTP2. Like if you have seen my HTTP2 video, there is a window frame and setting updates. Whenever you can basically use flow control, or you can just tell the server to slow down the data, right? Same thing happens here. In the congestion control, it's a way for the sender to adjust the data sending rate based on the feedback from the network. So it prevents packet loss, delay, and overhead. So QUIC maintains a congestion window which defines how much data can be in flight before waiting for acknowledgement. So as in HTTP2, there is also an entry, right, which is used to find out how much data can be sent before the data is being acknowledged in a stream, right? Here the mechanism is still same. So if the acknowledgement occurs, then the congestion window grows, like it starts sending data faster. But if the packet is lost or some lossy transfer has been detected, then the window will shrink. So it will slow down the rate the data is transferred between the streams. Same thing happens in the HTTP2, right? Window updates happen. This client sends the window update based on the packet is lost or not, and the data will be sent accordingly between the server and the client. So simplified setup on the connection. So as you know, in HTTP 1 and HTTP 2, they both use TCP as an underlying protocol, right? So the TCP connection should happen before uh, before a client can start sending the request to the server, right? So if you are using HTTPS in HTTP 1 and in the HTTP 2, by default works on HTTPS, right? By default it is a secure protocol. So the connection setup was bit complicated than HTTP 3. So in HTTP 1, let's say we are using HTTPS. So two handshakes will happen, one with TCP handshake and one the SSL handshake. So as you know, in TCP handshake, first client will send a SYN packet to the server. Server will respond back with the SYN acknowledgement packet, and then client will acknowledge that it has received the SYN acknowledgement packet and the TCP connection is successful. Then for HTTPS, an SSL handshake will happen, where client will again send a hello packet to the server. Server will send the response along with the certificates, and then the key exchange will happen between the client and server, and then the connection is set up for SSL for encrypted transfer and all. So this is the whole process that happens before a communication starts happening between a client and server, right? But HTTP 3 has simplified it. So whenever a connection needs to happen in HTTP 1 or HTTP 2, this process has to happen. Like for opening a new connection, all these requests will be made by the client and server. But in HTTP 3, things have become simpler. So now, initially, when a client tries to create an initial connection, the first connection on a server or on a domain, some packet transfer will happen. So let's say for the first connection that the client is trying to make with the server, it will just send the initial packet. Then the server will respond back with a message as well as some encrypted extensions, or you can say synchronization tokens. There are different names for that, or resumption tokens. Those tokens are stored by the client, and client will respond back to the server that it has successfully received the tokens and all, and it will finish the request. Once the connection has been made, then client can use the connection to send the frames on that connection, right? Creating the streams and send the frames on that connection. So as we know, in the HTTP 1, HTTP 2, if HTTP 1 tries to create another connection with the server, it still goes with this whole process again. Even if the first connection is already there, it will again go with this whole process. Like it will again make this call, a SYN call, and make the TCP. It will do the TCP handshake, then SSL handshake, and everything. But in this case, once the connection has been set up by the client on a particular server, if it wants to create another connection, for example, let's say these encrypted tokens sent by the server in the first connection, it's stored by the client, right? So let's say the first connection has been set up between client and server, data communication happened, and let's say after it is completed, the connection got dropped. Now client wants to again connect to the server for some another request. Then it can use that encrypted token that is stored by the client by the previous connection, and use that token to directly send data to the server instead of doing this whole thing again. So because the token is already present on the client side, it can use the same token, and server will look into that token, and it will just allow the request. If the token has expired, then this process will get repeated, and otherwise there is no handshake required until unless the token is valid. So this is what I have summarized here. When the client has connected to the server before, it caches cryptographic information, which is called resumption token sent by the server in the first connection, which is sent in the first response from server to the client, and it can resume the session using that token only. After the first connection has been made, and if the token is valid that is present on the client side, client can start sending HTTP request immediately and without waiting for the server response. Even if the handshake finishes in the background, client has already started sending. So if required, for example, if the token has been invalidated, the connection can happen in the background, the handshake can happen in the background, but client will start sending the data. Server verifies the token and resumes the session using that stored cryptographic state. Yeah. So next feature provided by the HTTP 3 is connection migration, which is not present in HTTP 2 and 1. So It's a unique powerful feature of QUIC, and by extension of HTTP3 it allows a client to seamlessly switch IP address on the network during an active connection without breaking it. So in HTTP 1 and 2, if you try to switch your network, right, it will break the connection and it will create a new connection when you come back online or switch the IP address, right? But in this HTTP3 allows you to migrate your connection over a network, over an IP address. So TCP connections, as we know, are bound to an IP address, a port, and a destination IP and port, right? So when you create a TCP connection, you need two things to reach to the server, right? An IP address and on what port the process is running, right? So it is bound to that these two things. So if your IP address changes, for example, if your IP address change or the port changes, the connection will break and a new connection needs to happen, right? But here in the QUIC, it generates a connection ID for every connection it is making. So instead of using IP address and port only for a particular connection, it also generates a unique connection ID for each connection, and each connection can be identified that unique connection ID not just by IP or ports only. So if the connection ID stays same, even if the IP and port changes, server can route packets based on CID, not the IP. So here QUIC not only use the IP and port, that is the default address of a server, the raw address of a server. It can also use the connection ID that it generates while creating a connection to send the data. So even if your IP address or a port changes in between, right? Even if the connection is same, so connection ID will be same, right? It will just say that send this data on this connection ID. Since the connection ID is same, but the underlying IP address and protocol has changed, the data will be going through the same connection, but on different IP, using different IP address. So example scenario, a user opens a video stream on mobile while connected to Wi-Fi. They walk outside and switch to mobile data, changing their IP address. So switching your network will change the IP address, right? So QUIC will detect the change and keep the same connection ID and send the packet from the new IP. It informs the server of the change using a patch challenge frame, and server responds with path response and continues to the session without breaking. So to explain it in a simple language, whenever you tries to change a connection, there is some frame transfer happens between a client and server. In the path challenge frame, client will inform the server that there is a connection migration needs to happen, and server will respond back with the successful response in the path response frame. Once these are transferred between the client and server, the connection migration is successful, and there is no handshake or no loss of session. No loss of session will be there. No handshake is required to create a new connection, and there will be no interruption, and data will start coming on the new IP address. So next topic is protocol ossification. This is actually a problem with the changing protocols. So protocol ossification says nowadays we are changing protocols a lot, right? So whenever let's say there is already a setup. Let's say there is a server, there is a client, there is a server. When the request goes from client to the server, there are a lot of black boxes in between, right? Like load balancer, server registry, CDNs, and API gateways. Like lots of black boxes are there in the between, right? So after going through all these the request reaches the server, right? So let's say all these boxes that sits between our client or server, let's say these are all the boxes, they needs to be aware of the protocol that is being followed while transmission, right? So let's say as HTTP2 is not backward compatible with HTTP1, so let's say there is a load balance. Let's take an example, and let's say there is a client, there is a server, and there is a load balancer. Let's say load balancer is only aware of HTTP1 rules. It is expecting a text-based header and body and everything. So now in HTTP2 there is nothing like text based, right? It starts sending frame, there is stream, and each connection there will be multiple streams, and parallel requests will be going on same connection. So it's not backward compatible with the HTTP1, right? So as we have updated our client, we have updated our server, but our load balancer is still expecting the data in HTTP1 format, right? In the text-based format. So it will not understand the new data coming in HTTP2. It will not understand those frames and everything. So this is called protocol ossification, because nowadays protocols are changing very fast. So server and clients can be updated like really fast with the changing protocol, but it's difficult to update these black boxes that sits between the in the internet. It is difficult to update them every time a change happens in the protocol. So such traffic is just dropped or delayed by them. So as load balancer will not understand this type of request, it will just drop them or delay them. So this raises the problem of protocol ossification. So QUIC tries to resolve this problem using its security and TLS layer. So with QUIC, the security has been merged with the TLS 1.3 as a part of the protocol, and this is no longer a multi-layer approach. In this, QUIC connection means doing cryptography and security with TLS. This prevents ossification as after the is making sure the QUIC has all secure properties of HTTPS. So QUIC has integrated with TLS, and it does cryptography on all the data that is being sent between a client and the server. So in QUIC, uh, everything is encrypted, like except a few metadata, I guess. For example, like packet number, length, connection ID, spin bit. So these packet number, length, connection ID, spin bit, all these things are like there from a very long time. So these are expected by your block boxes. So things like that is like common metadata. Apart from these initial info, everything is encrypted in QUIC. So multi-boxes can only peek into the frame types or stream IDs, or they cannot peek into these frames types and stream IDs. Like they are only interested in the metadata, that some request is coming, this is the connection ID or something, this is the packet length. So they do not peek inside the stream IDs, or peek inside the what how the data is being transferred, like what is the frame type or what is the stream ID or header fields. Like they do not care about that, right? So as the data is encrypted, they just ignore it, and hence it helps in preventing the ossification in HTTP3. So in QUIC, there are some strict rules created for resolving this problem. So it is said that if you see any unknown frame time, you must ignore it. So all the black boxes, when they will see some unknown frame or some unknown data coming, unknown way of data coming from the client or the server, they will just ignore it, and they will just move it forward instead of failing it. Explicit version negotiation. So let's say there is a black box, so it supports some version, so there could be a problem of version support as well, right? So let the HTTP3 it sends some data, but the black box is saying I do not support this kind of version, and it will just reply back, I will just support this type of version, right? So in this, version negotiation can happen between a black box and the client or server, from whatever the negotiation is happening. Either if the server is sending data, then negotiation will happen with the server, and if the client is sending data, then the negotiation will happen with the client. So this enables clean evaluation without ossification at the version level. Spin bit. So QUIC designers knew operators want observability, right? So uh, so as the middle operators, they just want to observe that uh, how much time a request is taking to come back from the server, all those things, right? They just want to observe the traffic going between the client and the server, right? So instead of letting middle box peek into their intervals, QUIC exposes just enough metadata to in a controlled way. So as I have explained earlier, apart from some meta info like spin bit, connection ID, that is needed for this observability purpose, everything else is encrypted in QUIC. So that is why the middle boxes, they will just take whatever they need, and they will just ignore the rest. So they will not they will not concern about what is coming in the data, either it is a text base or it is a frame base. They will just take whatever they need, and they will just ignore the rest and forward the request. So once this is a grease, an extensibility trick in QUIC TLS 1.3, it starts sending fake or unknown values called grease. So when it sends a fake or unknown values, it is called grease. For example, a random result TLS cipher suits, or random QUIC transport parameters, or so well the implementation that are well managed and that are well maintained, they will just ignore unknown values training, so that the connection remains flexible. So if a middle box tries to block unknown values, it will break even the current traffic, and vendors fix it earlier. So this is all about the security in QUIC. Let's move to the flow control. It's still the same as we haven't seen in HTTP2. So QUIC also provides flow control stream level and connection level like HTTP2. As in HTTP2, you can have your weights and you can just tell on the stream level that this much amount of data should go in a stream, or you can just tell on the connection level that this much amount of data should go in the whole connection. So when you put a limit on connection, all the streams get affected, right? For example, let's say if you put a 10 MB limit on the connection level, then the whole connection can transfer data up to 10 MB, right? And if you put a limit on the stream, only that stream will follow that limit. Other streams are still they can send more data, right? So the same can be happened in the HTTP3. So if the flow control window is exhausted in HTTP3, sender must stop sending out on that stream, and receiver sends a max stream data frame to increase stream window, or sends a max data frame to increase the connection window. So in both the cases, either you increase the limit on stream or increase the limit on connection. That can affect your data transfer, right? So if the connection limit allows 10 MB, but if you want to increase the limit on stream more than 10 MB, then you have to increase the limit on connection as well, right? Because stream is under the connection. So that is why, depending on the scenario, either max stream data frame or max data frame will be transferred. So max stream data frame tells how much data can be sent in a stream, how much maximum amount of data can be sent in a stream, and max data frame tells that how much maximum amount of data can be sent inside a connection. So these frames travel according to the requirements, and they just increase the data flow within a stream or within a connection. Now let's go to the stream identifiers. In QUIC, and therefore in HTTP3, each stream has a unique stream ID, a number that helps identifying and manage that stream independently. Just like in HTTP2, there is a stream ID, right? That is used by client and server to assemble all the frames and know what frame belongs to what request or response, right? There is a stream ID in HTTP3 as well. So here streams can be unidirectional or bidirectional, or client initiated or server initiated. Here the streams can be initiated by both client and server, and data they can be configured so that the data can be transferred in a single direction or in both the directions. So the last two IDs of this 64-bit unsigned integers, they tell you what type of streams are there. So if the LSB bit is 0, then it is client initiated, and if it is 1, then it is server initiated. And if the MSB bit is 0, then it is bidirectional, and if it is 1, then it is unidirectional. So these two bits will tell you if the stream is unidirectional or bidirectional, or it is client initiated or a server initiated. Bidirectional streams are used for request response data like HTTP headers and body, where a request will be made by the client and data will be sent by the server. Unidirectional streams, they are used for control flow and auxiliary functions such as settings and server push and everything. For example, where the data doesn't need to be transferred both the ways, unidirectional streams are opened by the client or the server, and data is transferred on them. HTTP3 defines special unidirectional stream using a stream type identifier, which is the first byte sent on the stream. So there are different types of stream that are present in HTTP3. One is called control stream. So updates the exchange connection used to exchange connection by the HTTP control frames like settings, go away, priority update. So priority update, as you know, is a frame to increase the priority of a stream. Go away is to tell that everything is done, close the connection. Settings is used to send some setting info, as you have seen in the demo of HTTP2 as well, right? There was setting frame going from the NG-HTTP client to the server, right? To the H2O server. In the prioritization demo, if you will go back to my video, you will see that setting frames goes before the data start transfer between a client and server, right? So the same is here. Rules: each endpoint must open exactly one control stream. It must be unidirectional and sent as early as possible. Frames like headers and data are not allowed on the stream because they belong to the data request response pair, right? So they are not allowed on the stream. Only the frames that controls the flow, that provide some setting those are allowed on this stream as well. If multiple control streams are opened or wrong frame types appear, the connection is considered invalid and must be closed with an error. Now there is a push stream. This is used by the server to push some resources. Like as you know, in the HTTP2, server can also push the resources, right? Although this has been dropped from everywhere. The support has been dropped from browser as well as a node and everywhere. So same when the server push was for the server push in HTTP3, this kind of frame is used. It has a push ID and headers and data frames for the uh, headers and data frames are pushed in this stream. Only the server can open this type of stream. This makes sense, right? Because push will always happen from server to client, right? Client cannot send server to say server to push some data, right? Server will itself push some data like, in response of a request, some extra data. If it wants to push for the response of the request, then only the push stream will come into the picture, right? So it is only initiated by the server. Used only if the server push is enabled, and client uses cancel push to reject unwanted pushes. So if client wants that it doesn't want to get any push data, then it can use this cancel push frame to reject those pushes. QUIC encoder stream, as name implies, that it is used for sharing the encoder and decoder data. So it is used to send frames which will help in inserting new entries into the dynamic table, or tell the duplicate entries or update the table size. All the information that is related to the encoder and decoder of the QUIC, or update in the table, that travels through this stream. Each endpoint creates one QUIC encoder stream, and it is unidirectional. Only the sender writes and the receiver reads. QUIC decoder stream. So this is used to this carries decoder feedback for QUIC, like acknowledging header blocks or reporting decoding errors. For example, let's say client sends some decoding info to update the table, right? So server will acknowledge using this stream that it has received the blocks, or if it is not able to decode something, or it is finding some error in the data, then it will use this stream again to report those errors. So each endpoint creates one decoder stream, and only the receiver sends data here. So this is a table I have created to summarize the difference between all the HTTP protocols. So as you know, the underlying protocol in HTTP1 and HTTP2 is TCP, and in HTTP3 is QUIC with the UDP. Multiplexing, there is no multiplexing in HTTP1, and one request can go per connection. Yes, HTTP2 and HTTP3, they both allow multiplexing, multiple streams over one connection, and here are as well multiple streams over one connection, but they are independent of each other. Head of the line blocking at both the HTTP and the TCP level is present in HTTP1, but in HTTP2 it is only present at TCP level, and in HTTP3 there is no head of the line blocking because streams are independent in QUIC. Connection setup here is TCP 3-way plus optional TLS handshake, because TCP handshake will happen for every connection, and if you are using HTTPS like SSL certificates, then the optional TLS handshake will also happen. In HTTP2, as HTTPS is mandatory, so always TCP as well as TLS handshake will take place. But in HTTP3, as you have already seen, once the connection has been made, the session can be used again using that resumption token without any handshake, right? So there is one RTT handshake for the first time, then zero RTT handshake happen, and the connection resumed using that resumption token. Here encryption is optional. You can use HTTP or HTTPS depending on the choice, but here HTTPS is mandatory. Also in the HTTP3, it is always required using TLS 1.3, and it is by default built into the QUIC. There is no header compression in HTTP1, but in both the HTTP2 and HTTP3, header compression happens by HPEG and QPEG. Stream prioritization and flow control is not possible in HTTP1, but in HTTP2 and HTTP3, both of them are possible. It's complex stream rate prioritization in HTTP2, and flow control is on the stream as well as the connection level. Similarly, in HTTP3, it is simplified by priority update frame, and in the flow control, it is handled by QUIC transport level flow control. So both the options are present in both HTTP2 and HTTP3. Server push is not supported by HTTP1. It was supported in HTTP2 and HTTP2.3, but it has been the support has been dropped from everywhere, like in CDNs, from the node, from the browser, from everywhere. The support has been dropped. So it's not there anymore. But it was initially supported in both the protocols. Persistent connection, yes, you have to use a header in HTTP1, which is called keep alive header, uh, connection header with the value keep alive to make the connection persistent, right? And by default in HTTP2 and HTTP3, the connection is persistent, it doesn't drop. Connection migration is not possible in HTTP1 and HTTP2, but it is possible in HTTP3. Here, packet loss impact is same in HTTP1 and HTTP2, affects the whole connection. In HTTP1, you have to send the request again, as well as in HTTP2, all the streams are affected, right? But in QUIC, as the streams are independent, this only affects that particular stream. Browser HTTP1 is like a very old protocol. It's heavily supported everywhere. Every service supports it. HTTP2 is already widely supported in most of the places, and the HTTP3 is supported by modern browsers only, like Chrome, Firefox, and its support is growing day by day, but still not up to the mark with HTTP2 or HTTP1. Server support, all the servers support HTTP1, and HTTP2 is already also widely supported by servers, and HTTP3 is still going. It is increasing, and it's already supported by Cloudflare, Caddy, and Nginx with patch. Using CDNs and CDN, HTTP2 and HTTP1 are heavily used there, but it is being adopted by CDNs. HTTP3 is being adopted by CDNs nowadays. It's not as popular as HTTP2, but it's being adopted by CDNs. Okay, that's all for this video. I hope you liked it and you have a deep understanding of the three protocols and the difference between them. I'll see you in the next video. Thank you so much.